My name is Jeff Amelang. In this video I'll be demonstrating a 2D inverse kinematics solver that I wrote for CS455 taught by Dr. Mike Jones at Brigham Young University in spring 2009. There are many methods for solving the inverse kinematics problem. The solver implements the Jacobian transpose method in an iterative approximation. The goal of the solver is to bring the end of the links, or what's called the end effector, as close to a user-provided target as possible. You can think of it as a robot arm, though actually controlling a physical robot arm requires transfer functions, feedback, equipment, and all kinds of other things that make solving that problem orders of magnitude harder than this. This is just a simple series of links. The links are processed and loaded from a file with rather arbitrary and poor formatting. Once the links are loaded, the user left-clicks anywhere in the window to change the target. I'll turn off the visual debugging information until later. The inverse kinematics algorithm continually adjusts the angles of each link to try to minimize the distance from the end effector to the target. This is moderately interesting. Here on the right side are some ways of making it a bit more interesting. First, we will look at the link length scale adjuster. Though each length has a set length when the links are processed, we can adjust the scale of the links. Notice that the links still dynamically hone in on the target and just adapt to their new lengths. We'll leave the links long as it makes things easier to see. Second, we will look at the time increment adjuster. Though it may look that way, the links are not fluidly changing position. They are making discrete jumps, but very quickly, at about 10 milliseconds per jump. We can scale the time step down for fluid, but slower motion, or we can scale the time step up for more jerky motion. We'll return it to a reasonable value. Next, we will look at the angular limit of each link. In real robot arms, there are pretty much always angular limitations to the travel of any given joint. I'll turn on the visual debugging setting so that we can see the angular limits that we artificially impose on the links. They are currently at 180 degrees, so the arms are rather agile. For example, it can reach behind itself rather easily. Let's make the angular limit a little lower. Notice that the arm now bottoms out, and the arm can no longer reach behind itself. Increasing the angular limit back to around the original value once again allows it to reach. Next, we'll change the origin of the links, or the anchor of the first link. By right-clicking, the user can set the link's origin. Next, we'll look at two visual debugging tools. The green vectors are the vectors from the beginning of each joint to the end effector. The white vectors are the cross products of these green vectors and the z-axis, which is coming out of the screen. The longer the cross product vectors, the more that a change in that link will affect the position of the end effector. The more that the cross product vectors align with the vector from the end effector to the target, or the direction in which we want the links to move, shown in teal here, the more that a change in that link will bring the end effector closer to the target. Lastly, we'll try a new set of links and see a limitation of the algorithm that we implemented. This set has more links, and each link is the same length. An interesting phenomenon is seen with this set of links. This might be hard to see over YouTube, which would be rather unfortunate. When I click outside of the reach of the robot arm, the arm oscillates before it stabilizes. This is because after using the Jacobian to solve for each time step's angular changes, each link's angular change is multiplied by an arbitrary scalar. You can imagine that if this scalar were very large, the arm would never hone in on its target because each step would be far too large. Imagine trying to move forward and step on a dot 10 feet in front of you when the only way you can move is to jump 5 blocks at a time. This can be forced by adjusting the angular increment scale and can be seen better by increasing the time step. Here you'll see oscillations when I click on new targets. When the scalar is too large, the solution is no longer stable and major oscillations occur. When the scalar is too small, the links move too slowly for anyone except those with exceptional patience. This is an unfortunate aspect of the oversimplifications used in the algorithm, but luckily there are much better algorithms out there to solve this problem.